Okay, in this video, we're going to look at section 1.3 of the OpenStax statistics book. And we are going to learn about levels of measurement, some frequency tables, and relative frequency. So in this level of measurement scale, we have nominal, ordinal, interval, and ratio. They're kind of from the lowest level to the highest. Nominal scale is qualitative. We have categories, colors, names, favorite food. So you could jot down a few more that you can think of. Yes or no responses would be nominal. So things that you're naming, qualitative data. They're not in any particular order, like team numbers, like on the back of your shirt. It's not really ordinal at all. It's just naming the person by a number. Trying to classify people according to favorite food doesn't really make sense. Putting pizza first and sushi second is not meaningful. You can later, we'll look at like Likert scales and things like that. Like, oh, what do you like better, pizza or sushi? You know, ordering things on a scale of 0 to 5 and things like that. Nominal scale data cannot be used in calculations. List out a few examples that you can think of for nominal data. You can pause the video and do that. Ordinal scale. Data that is measured using an ordinal scale is similar to nominal, but it can be ordered. For instance, we have the list of top 5 national parks in the United States. So this is where it's different. You're ranking things. But there's still not measurable differences between the data. Another example would be a cruise survey. This is where we take that nominal and we kind of go the next level up, and we're doing the scale of 0 to 5, like I was saying earlier. From most desired, least desired, things like that. Again, it cannot be used in calculations. Interval scale. Data that is measured using interval scale is similar to ordinal because it has a definite ordering, but we also have differences between the intervals that can be measured, though the data does not have a starting point. So there's not a true 0. So like temperatures, because we have Celsius, Fahrenheit, you can go above or below 0, and differences make sense, but you wouldn't have like twice as much or something like that. And we don't have the 0 just being a nothing. Interval data can be used in calculations, but one type of comparison cannot be done, which is like having, multiples of it. There's no meaning for ratio. So jot down some examples you can think of. Or questions that you might have, you could put in the comment section of your note submission. If you just put your questions on the sheet itself, I may not notice it, but if you put it in the comments, then I can address that, or something you just want to discuss. It'd be good to put there. Ratio scale. That is gives you the most information. Ratio scale data is like interval scale, but it has a 0 point, and ratios can be calculated. For example, for multiple choice statistics, final exam scores at 80, 68, 20, and 92 out of a possible 100 points. The exams are machine graded. The data can be put in order from lowest to highest. We have differences between the data that have meaning, and ratios can be calculated. And we have the smallest score is 0. And we could talk about like 4 times better, double, triple, those kind of things. So it has all the other things and more. So think of things for the ratio scale that you might have ideas about. Frequency and frequency tables. So frequency is just the number of times a value of the data occurs. The sum of the values in the frequency column represents the total number of values included in the sample. So that would be our N. Relative frequency is the ratio or the fraction or proportion. Sometimes we write it like just as a decimal, sometimes a percent, sometimes as a fraction. It really depends. The number of times of a value the data occurs in the set of all outcomes to the total number of outcomes. So you're just going to divide the occurrences over the total to find the relative frequencies. We can write them again as fractions, percents, decimals. Cumulative relative frequency is when you're adding up the prior value and so on and so forth. We'll see some examples of that. You could do that with frequency as well. Just a note, because of rounding, the frequency column may not always sum to 1 or 100% if we're looking at percentages. And the last entry in the cumulative relative frequency column may not be 1. However, they should be close. So if you're just a little off, don't worry about it. It's just due to rounding. If it's way off, then you should reassess what you did. So here's a frequency and relative frequency table. So usually we start with just the frequency. We might collect data for that. Sometimes we just have it given to us as the decimal or relative frequency. But this is heights in inches. And a lot of times you have like this kind of edge here are the boundaries. So this one is 59.95 to 61.95. So it's kind of getting that little bit on the boundary. So this represents the heights in inches of a sample of 100 male semi-professional soccer players. And we would have 5 in that first row. Relative frequency, we would take 5 divided by 100, get 0.05. Cumulative relative frequency for the first row is just 0.05. And then you can see how they add up. The next one, we have 61.95 to 63.95. Frequency is 3. Relative frequency is 0.03. And then to get the cumulative, you add that prior row. And so that would be 0.08. So I'm not going to read through all of those, but you can take a look at that, and then we'll have some questions here. So here's the questions, but I did kind of put the slides together here so we could look at them side by side. So if we have the question, the first one is the percentage of heights that are from 67.95 to 71.95 inches is, and so you're going to look at the chart and you're going to check out where we have 67, let's see down here, on the left, 67.95, and that's going to go all the way up. We want to have 73.95. So we want how many, or what the percentage is for that. So take a moment and work that out. The relative frequency is already done for you, but we don't want to use a cumulative because we're not doing all the ones prior. We're just doing those here. So 0.17 plus the 0.12 plus the 0.07. And I just realized A actually only goes to these two, 71.95. Sorry about that. So the first question, A, is 0.17 plus 0.12. You'll get 0.29, so 29% for this A. Part B, we also want to go all the way up to 73.95. So we'd add on that 0.07 and we get 0.36 or 36%. So the question actually asks for the percentage, so you're going to convert your decimal to a percent. So go ahead and fill those out. And then think about what the data are, what kind of data it is. Is it qualitative, quantitative, and which kind of quantitative, if it is? And then describe how you would gather this data to be representative. Like, what's just an idea that you could use from things we learned in the prior lessons. Okay, and just a note to remember, frequencies are the numbers, and the relative frequency is the ratio or the, proportion, percent. Okay, so pause the video. Okay, so hopefully you've had a chance to just jot those down. And here is the answer key. So this is just a write-up of what we talked about. Here are the answers. So we already did A and B is 29% and 36%. C would be 77%. So we're looking at everything past that 65.95. Number of players between 61.95 and 71.95. So this time it's asking for the number. So make sure you don't just give the percentage. You want the actual number. So that would be 87. The kind of data is quantitative continuous. Describe how you would gather this data. One idea would be to get rosters from each team and choose a simple random sample from each. You could use the random number generator. Also you could just put all the numbers and names in a hat and pull out some. That would be another way to do it. Okay, for this slide, we're looking at frequency tables again. This one is the rainfall, annual rainfall, and a sample of towns. So here's the questions that go along with it, and you can go ahead and work those out on your own. We have the questions are: try at 1.14, find the percentage of rainfall that is less than 9.01. So use the table, and then you're going to have we're looking for percentage, so you can just use the relative frequency. And for 1.15, the same thing, you're doing it in between those values. And then 1.16, you got to remember to use the number. Just use frequency because that's what the question's asking. So just go ahead and take a moment to work those out. Pause the video. Okay, so here are the answers. Hopefully you had a chance to work that out. So try at 1.14 is 56%, 15 is 64%, and 1.16 is 28 towns. Here's another table that you have for total number of fatal motor vehicle traffic crashes in the United States for the period from 1994 to 2011. And if anyone needs the tables like done out differently for them, let me know. I could try to make those more accessible if needed. So here are the questions side by side with the table. So this is a problem for you to do on your own. You'll be seeing more and more of this. So I collect all the notes, all the example stuff too, but primarily I want to make sure you know how to do some problems and you're confident. If you have questions on those, if you're not getting them right, write in the comments of your Canvas submission. Don't just put it on the submission itself. You want to be able to see it right away. So pause the video and jot those down. I'm going to reveal the answer now. So here's the answers. We have the first one, the frequency is 190,800. And just as an aside, just to see the percentage, 29.2%. So you can tell, like, it's really probably more helpful to see the percentage to be relative to what the other numbers are. So we don't have the same totals for everything. And B is 24.9% for after 2006. C is 39.8%. D is 4.6%. And E is 75.1%. Section 1.4, I'm going to just put right in with this video. Experimental design and ethics. You can identify the practice and ethical concern that arise when conducting a study. And we'll just do the best we can given the parameters of the course. It is an introductory course, but if you're doing anything as a study and you're not sure if it's okay to do or not, let me know. And we could talk about it. The purpose of an experiment is to investigate the relationship between two variables. When one variable causes change in another, we call the first variable the explanatory variable. You may have heard of that called the independent variable. It's usually the X variable, but not always. Sometimes things get swapped around for whatever reason, but typically we call that X. The affected variable is called the response variable, and that would be your dependent variable, and we usually use Y. And it would be your vertical axis. In a randomized experiment, the researcher manipulates the values of the explanatory variable and measures the resulting changes in the response variable. The different values of the explanatory variable are called treatments. An experimental unit is a single object or individual to be measured. So a unit could be a person. Additional variables that can cloud a study are called lurking variables. In order to provide the explanatory variable is causing a change in response variable, it is necessary to isolate the explanatory variable. So there's all sorts of other factors that can happen. We call that confounding a lot of times too. So we really want to try to minimize that. It's hard, especially in like observational studies or things like that, where it's not a controlled lab. It's really hard to get rid of all the variables, lurking variables. The researcher must design the experiment in such a way that there is only one difference between groups being compared: the planned treatments. This is accomplished by the random assignment of experimental units to treatment groups. When subjects are assigned treatments randomly, all of the potential lurking variables are spread equally among the groups. So we can't get rid of them entirely, but at least since we've randomized who gets what, like usually there's a placebo and there's a treatment, and it'll be all mixed up. So that minimizes problems. When participation in a study prompts a physical response from a participant, it is difficult to isolate the effects of the explanatory variable. To counter the power of suggestion, we have a treatment group that is a control group. They're given a placebo, which means it's fake. It's like a sugar pill or something that looks and seems just like the treatment. Could be a number of different things. Could be a shot, could be a pill, cream or something, food, treatment that cannot influence the response variable. So it's really not going to do anything. So you don't want to have it be too close to the real thing or close at all to doing something that the real thing would do. The control group helps researchers balance the effects of being in an experiment with the effects of the active treatments. So if you're participating in a study and you know that you're receiving a pill which contains no actual medication, then the power of suggestion is no longer a factor. So blinding in a randomized experiment preserves the power of suggestion. So you wouldn't know you're getting the pill. So in a blinded study, the person or the experimental unit, does not know they're receiving the placebo treatment. Double blind is one where the subject or unit does not know, and also the researchers involved do not know. The widespread misuse and misrepresentation of statistical information often gives the field a bad name, so this is part of the ethics. We'll talk about these things more as they come up, but we're just getting the vocabulary out there. There's more details in your book too. Some say that numbers don't lie, but the people who use numbers to support their claims often do. There's a lot of times some bias. Who's funding the study will be looking at some articles and talking about things that could be problematic. Many types of statistical fraud are difficult to spot. Some researchers simply stop collecting data once they have just enough to prove what they had hoped to prove. Sometimes they also do like just smaller studies and act like they're, have these great findings, but then you realize it's more anecdotal. They don't want to take the chance that a more extensive study would complicate their lives by producing data contradicting their hypothesis. So here's like a scenario, case for you. You are concerned about the effects of texting on driving performance. Design a study to test the response time of drivers while texting and while driving only. How many seconds does it take for a driver to respond when a leading car hits the brakes? So here's some questions to consider. Describe the explanatory and response variables. What are the treatments? What should you consider when selecting participants? Think about if your research partner wants to divide participants randomly into two groups, one to drive without distraction, one to text and drive simultaneously. Is this a good idea? Why or why not? Identify any lurking variables that could interfere with this study, and how could blinding be used in this study? So pause the video and jot down some ideas. Just kind of brainstorm, just think of what you can with the best you know how to do right now. That's fine. And then we'll go through it and I'll show the answers. Okay, I'm going to reveal the answers now. So explanatory and response variables. Explanatory is the presence of distraction from texting. Response is the response time measured in seconds. The treatments are driving without distraction and driving while texting. What should you consider when selecting participants? You want to know if they regularly send and receive text messages, how long have they been driving, what's the age, do participants have similar texting and driving experience? Because if you have a really big disparity, you may not be measuring the right thing. Like if you're just like a lot of people are new to driving, that could be different, this and that. So those are just some ideas to think about. If your partner wants to split the groups up and one's gonna have distracted driving and one's not, what's ideas on that? It's not a good plan because it compares drivers with different abilities. It would be better to assign both treatments to each participant in random order. I also think you do have to think about the ethical ramifications of this. Like if you're telling people to text and drive and they go out there and do it, you know, we gotta have a controlled environment where they're not gonna hurt themselves or somebody else. Identify any lurking variables that could interfere with this study. And ignore that one there. Possible responses for things that could interfere is texting ability, driving experience, and type of phone. And then how blinding can be used. The researchers observing the trials and recording response time could be blinded to the treatment being applied. Okay, here's another one to try. Describe the unethical behavior, if any, in each example and describe how it could impact the reliability of the resulting data. Explain how the problem should be corrected. So here's the study. A study is commissioned to determine the favorite brand of fruit juice among teens in California. The survey is commissioned by the seller of a popular brand of apple juice. There are only two types of juice included in the study, apple juice and cranberry juice. Researchers allow participants to see the brand of juice as samples are poured for a taste test. Well, hopefully you're thinking, there's some problems with this. 25% of participants prefer brand X, 33% prefer brand Y, and 42% have no preference between the two brands. Brand X references the study in a commercial saying most teens like brand X as much or more than brand Y. So think about that and just describe if there's any unethical behavior and if you can correct it. So pause the video. Okay, so hopefully you've had time to go through these questions and jot down what you think. So here's the first one. If a study is commissioned by a company, this is not necessarily a problem. It should be monitored carefully, however, to ensure that the company is not pressuring the researchers to return biased results. If there's only two types of juice, if they really want to determine the favorite brand of juice, then they should ask teens to compare different brands of the same type of juice. So that gets rid of some lurking variables there and confounding. Choosing a sweet juice to compare against a sharp flavored or tart one like cranberry juice is probably not going to work too well. if they can see the brands, they could be biased by the knowledge, just thinking like, I like that one better, it's more expensive or whatever. And the way they depict it. The commercial tells the truth, but not the whole truth. It leads consumers to believe that brand X was preferred by more participants than brand Y, while the opposite is true. So that is it for the chapter 1 slides, other than here's some links if you want to look at the chapter review and key terms in your book. You can also get to that by your table of contents in your book. And then here's acknowledgments, which this is an open source book, and it has been created, and then I've changed it around a little bit here and there, added in some things and formatted it differently. And I hope that helps you understand the chapter and be able to get your homework done and your activities. Have a great day. Let me know if you have any questions. Remember to write in the comments box of your Canvas assignment after you submit. If you want me to get right back to you and to be able to see it easily, using the comments is what I really need to have.